So here's my talk. Okay, so let me first start by thanking the organizers for giving me the opportunity to talk here, and maybe this is because original abstract which I submitted, there was not so much relation actually to the Aharonov-Bohm effect, but in the end we mentioned something about weak values, which was at that stage still kind of well, it was not done yet, but okay, they still selected this thing, my abstract, to give a talk here. So we really had to do something to make actually a relation to the weak values, but we did this. And it's not still in the title, but I just want to say here that mainly to emphasize the collaboration with my postdoc, Adam Bednorz, on this topic, which is mostly his invention. Okay, so the relation to the Aharonov-Bohm effect is, well, the Aharonov-Bohm effect is a paradox, and what I'm going to present to you in the following, in the end, I also want to present you a paradox and show you how to resolve it. So, okay, you all know what a paradox is, and we heard, you know, that there are other paradoxes, and paradoxa, and in particular, there are a number of them were presented 2 days ago in the talk by Lev, and I stopped counting at some stage. I don't know how many he presented in that talk. Okay, and in the paradox I want to address here is in the connection to this weak values, which were nicely also already introduced by Yuval Geffen in his talk, and also by Alessandro Romito. Okay, and the paradox here is obviously that if you measure something via this weak value protocol, you can obtain results which are outside of the spectrum of the operator. Now changing slides, it's probably like this. Okay, so let me repeat again. I don't really repeat the protocol here, but the outcome is that if you prepare the system in some initial state, and you then make a weak measurement of some variable A, and then you make another strong measurement, which is a post-selection, projective measurement of some final result F, you obtain the weak value, which then is this a number, and as you see, it's not obviously real, and it can be a complex number, and it can in particular also be outside of the spectrum of the operator A. Okay, and one can obviously generalize this to more. This is the time. Okay, very good. So this includes the discussion time. Okay, I have 20 minutes. Oh, I have 20 minutes. Oh, no, very good. But I also kept to Lev's advice to kind of reduce the number of slides to a minimum to leave time for discussions. And anyhow, one needs usually longer than one expects. Okay, so okay, one can obviously generalize this to more general states, which was also mentioned already. For example, if one has not a pure initial state but some density matrix, then one can obtain a weak value just like that. But okay, and this will be important later on, because we are interested in also in measurements of correlation functions in Mesos-copic circuits. So we measure current correlation functions, and then these states are usually many body states. So you have Fermi seas around, and so one has to deal with a density matrix. Okay, now there's another way to treat weak measurements, which that's why where we started with actually, and now I want to make the connection of this method or this to the weak values. So this is the so-called positive operator valued measure, and so it works like the following. It's also a way to introduce a weak measurement into quantum mechanics. Actually, quite a general way. So if, and it can also be used to kind of measure, for example, non-commuting operators and things like this. I mean, as far as one can, at least. And so it works in the following way. One defines a set of operators, K of A, which have the condition that they resolve the unity like this. And then the POVM protocol says that if you now do a measurement of A, what you do is you change the density matrix with this so-called KRAUS operator, K of A, in such a way. And then you have the probability to find A to just taking the trace of this new density matrix. Okay, and what is important, another very important ingredient here is the Naimark theorem, which says that this is not something, so this is very general, and it really corresponds also to a quantum mechanical projective measurement. So there's nothing, not a new, not say a contradiction to the projection postulate, but the point is that in this way it corresponds to a projective measurement, but in the Hilbert space, which includes some detector. But the important thing is you do not have to include you don't have to say anything about the detector. You just know that it exists, provided there's no initial correlations between the detector and the system. I mean, it's probably to some people pretty well known, but say to people in Mesos-copic physics, for example, it's not known really, this method. Okay, and one important thing is also, I mean, one can now continue this and actually do several measurements. Okay, so you can introduce another set of operators, K of B, and perform a second measurement and a third one, and then you kind of, in an obvious way, you just get the new density matrix after the second measurement, which has again these two KRAUS operators. And then you find the probability to find B and A just in that way. Okay, and you can continue this obviously to a number of for 2 more measurements. Okay. And in the following, in particular, in the weak value, for example, we are interested in 2 measurements only. Okay. Now, let me give you an example of this KRAUS operator, which kind of some interpolation between a weak measurement and a strong measurement. So one can introduce a KRAUS operator, and because it's it's so general, it can be anything. Maybe the physical implementation is not so obvious of that operator in a concrete system, but you can take it and it fulfills the requirement, and it contains a parameter lambda. So you see the Gauss like a Gauss function. So you see that in the limit, when lambda goes to infinity, this actually corresponds to a projective measurement, or will correspond. I mean, you have to do all the procedure. And if lambda is very small, we come to a weak measurement, but then this thing will add actually a large noise of the detector to the system. And this is the limit of also we take in the weak value. Okay, and now using this operator, you find for the density matrix after the measurement that you can write it as a convolution of some quantity, some operator with this Gaussian noise. So this is just, you add this Gaussian noise, and now you have also some operator. But the point is that this is not necessarily a density matrix. So it's let's call it a quasi-density matrix, which has now, when you do all the algebra, which is not very difficult in that case, has this form. So this is a quasi-density matrix, so it kind of contains the original density matrix, and here are some remnants of this KRAUS operator and so on. And if we just do this one measurement, actually you just calculate the probability. You find actually that if you take the trace of this thing, it's actually totally independent of this parameter lambda. And of course, this means in this case we can assign to this quasi-density matrix a probability, and this is fine. Okay, and we have, of course, in addition, in a real measurement using this KRAUS operator, we have in addition the Gaussian noise. Okay, and let me note here that in the limit of this lambda going to 0, which corresponds to the weak measurement, as I told you, this goes to a delta function, and the lambda actually drops from this expression. Yeah, so this becomes a delta function. So already at this stage, it drops from this expression in that limit. So I can take the limit lambda going to 0 well defined for this quasi-density matrix. Okay, now we come to the second measurement and approach the weak value. So now let's apply a second measurement of B, and now we can do the same thing. Now we get, of course, Gaussian noise due to the measurement of A. We get Gaussian noise due to the measurement of B, but we get a quasi-density matrix which has this form, and now we can define a quasi-probability by just taking the trace of this quasi-density matrix, which in this case, by the way, is again independent of this lambda parameter of the second measurement. Okay, and now at this stage we can make the connection to the weak quasi-probability by saying that we can now define a quantity which we call which I called weak quasi-probability, defined like this. So this is actually the post selection here. So I take a certain BF, yeah, a final result, and I divide here by this factor. This is just similar to this weak value expression. And now in this limit, actually, I obtain the weak value using this weak quasi-probability just as a usual expectation value. So I just take, this is, you know, if this is the formula you have for any expectation value, but now this row of A, this row of, which depends on lambda A in the limit of lambda going to 0, is not a real probability, but it's a quasi-probability. So, for example, it can be negative, and this explains how you can get, of course, values which are completely outside the spectrum. It's kind of an alternative view, but in the following, in this context of current measurement, I will use this quasi-probability rather than weak value. Okay, so this is the connection of this approach using POVM to the weak value. Okay, now I want to go to Mesos-copic physics and ask what can we see some of this strange thing, let me call it strange things, also everything is just quantum mechanics, but these seemingly paradoxical things like weak values or negative probabilities in a measurement, and how to see them. And for that we are going to a time-resolved measurement of a current. And so the current is some operator which at different times does not commute. And well, currents can be measured, average currents can be measured standard, but kind of time-resolved current measurements are more difficult, and in particular if with very high time resolution at high frequencies, this is also difficult. I just want to mention that we have actually shown last year that one defines a certain generating functional. The point is now here the number of measurements, the sequence of measurements is just, you know, the time coordinate. Okay, so such a time-ordered expression here of this exponent is like a sequence of measurement. It's like a continuous measurement. Of course, we are finally interested in the continuous limit. And then, of course, you have all these problems of you measuring non-commuting operators at the same time and so on. So actually, the point is that you can define such a generating function. It has been used in Mesos-copic physics, counting statistics before, but this actually corresponds not to a real probability, but exactly to such a quasi-probability as I have shown you before. Okay, so this defines only a quasi-probability. And if I do this POVM, for example, I get this in a certain limit, and I get an additional large Gaussian noise, which kind of makes all things positive, and so on and so on. But we also can take the other limit, which is probably also interesting in the experiment. Okay, now let me, instead of doing this complicated, here you have to talk about path integrals, okay, functionals and so on. Let me go to a simpler case. Sorry. I wanted to mention one thing that one can actually, I wanted to make the connection to the experiment here. There are experiments, in particular by Bertrand Ruelet and Jean Gabelli in Paris. They are doing high-frequency measurements of current and higher-order correlators in the quantum regime. And I have shown here just some results, and it's, well, you can, one technical thing which I completely skip over here is how to calculate higher order correlators, because this is non-trivial, in particular if you get to fourth order correlators, as I will show in a second. This is highly non-trivial to calculate them. And there are just some results which are presented here by theory. So, for example, for the average currents, you get some. This is Ohm's law, yeah. For the finite frequency noise. So this is a symmetrized correlator. For those people who kind of in that business, one obtains in the zero temperature limit something which contains a quantum feature here when the frequency is equal to the applied bias voltage, and one can also calculate this for a tunnel junction for the third correlator. And I only just mentioned this here and just show the theoretical plots, the theoretical results, because all these numbers are actually confirmed experimentally. So there's a lot to talk about these experiments. It's very complicated experiments, but the experimentalists are very, very brave and, you know, do this for months and months work in the lab to extract such numbers. Okay, now I want to kind of show you how in a high frequency current, or in some high time resolution current measurement, I can kind of construct the paradox. And the idea is, so let's assume kind of two instants of time. So we kind of define the current, some kind of charge which is measured over some instant of time of length delta, and at two time instances. And let me call this A and this is B. Okay. So okay, maybe I've messed up the orders of A and B in this talk somehow. I just see now, but because previously I was talking about first measuring A and then measuring B. Now it's just the opposite around, but it doesn't really matter here. Okay. Okay. Now we can do this POVM thing and define this generating function in the limit that these lambda parameters which are introduced in these KRAUS operators go to 0. I obtain a generating function which now has exactly this form. So now I don't have this integral anymore, but this is exactly the form of the generating function, which generates, but unfortunately it just generates me a quasi-probability, okay? But now the question is, how do I kind of make this quasi property visible? And the answer is I have to actually to go to fourth order correlators, okay? So, and fourth order correlators can be calculated something like this. So I measure, well, this charge squared at some time t and correlate it with the time 0. This corresponds now to a squared b squared. And okay, again, at some stages here there should be operators and at some stages not. Please forgive me. But the important point is now once I have defined these two operators, I can construct this paradox by looking at that every quantity should obey this, every probability should obey this Cauchy-Schwarz inequality. X squared, y squared expectations are larger or equal to xy squared average. Okay, and now let's take the operators I've just defined previously. So I take x is a, b, y is b squared, for example. Then I actually find that using this quasi-probability, I find that x squared is equal to 0. This is still no contradiction. But I also find that xy averaged with this quasi-probability gives something finite. The negative sign here is not important. It gives something finite. So this side is 0, this side is finite. So I have a paradox. And the paradox is that, well, I mean, for a real probability, I would not expect that. But for this quasi-probability, it happens. In a real experiment, of course, I should not forget that I measure these quantities plus the Gaussian noise. So in an experiment, I would have to be carefully subtract the Gaussian noise of the detector, yeah, not the intrinsic noise, but the noise of the detector. And this is the last slide. I'm just... Okay. Okay. So this is the way to kind of see this property by measuring these quantities here and show that this inequality is. And this is the summary. Basically, I have shown you the relation between weak values and this positive operator valued measure. I have introduced this quasi-probability, and in addition, one should keep in mind that one has this Gaussian offset detector noise, and I have constructed some paradox which goes via evaluation of Cauchy-Schwarz inequality, and this can be used as a signature. And some open question which we are going to address soon is kind of, can we express all this in terms of some weak value? Thank you for the introduction.